Okay, awesome. Okay, so yeah, thank you very much for inviting me to talk. So I'm going to be talking about this paper called Quantum Minimal Surface from Quantum Error Correction. Came out in archive towards the end of last month, and this was work with Chris Akers, who's a postdoc at MIT. So it's a sort of interesting paper because the motivation is essentially entirely from quantum gravity, high energy physics. But the actual content of the paper is essentially entirely a paper about finite dimensional quantum systems, about quantum information, essentially, quantum error correction, things like that. So it means there's sort of a slight, it's a hard paper to present because there's sort of a lot of ideas from a lot of different areas that need to be communicated. But anyway, I will do my best to do that. Please ask questions if I say anything that's unclear or not familiar to you. Okay, so let's start with quantum minimal surfaces. So this is going to be practically the only true high energy theory statement in this talk. So if I have a static state or time reflection symmetric state in ADS CFT, then on the CFT side, I can look at the reduced density matrix of some subregion of the boundary, call it capital B. And then there's a prescription, a holographic entropy formula for what the entropy of that reduced density matrix is. Okay, and in this case, it's just given by a minimization over all sort of subregions of the bulk, which I'm going to call little b, some arbitrary subregion of the bulk, and then we're going to minimize the sum of two terms. The first just looks a lot like sort of a Bekenstein-Hawking entropy type thing. It's the area of the sort of edge of that region of the bulk divided by 4 times Newton constant. And then there's a correction, and that correction is in fact just the entropy of bulk quantum fields in little b. Okay, so it's the entropy of that subregion. So as I say, this formula I included quantum corrections, but on the other hand, I did assume that there's at least time reflection symmetry, or often you can consider things that are static. So in fact, for general time-dependent states, then really what you should be doing is sort of maximizing. You should compute this quantity individually in every possible Cauchy slice through the bulk, every possible time slice. And then to compare, you need to answer the question of which slice you should be using when you actually do this computation. And the answer is that you should choose the slice that maximizes this minimum generalized entropy, this minimum quantity. Okay, so you first minimize, and then you maximize overall the minimum. So that's the sort of real general formula. That's what's called the quantum extremal surface prescription. It's the one that's most commonly talked about these days. It's the most general one. But the sort of maximizing over time slice is going to be beyond the scope of this paper. I'm not going to try and sort of explain that at all, or have anything really to say about that. And this sort of quantum minimal surface prescription can get you a long way. You can learn a lot of stuff. So yeah, it's pretty good.
How did this formula make appearance when you look at the one you just showed?
So in fact, so the original thing that appeared did not include this extra term here. It was just this minimizing over areas, and that was by Ryo and Takinagi in about 2006. And then that classical formula got generalized to the time-dependent case by Hubani, Rangmani, and Takinagi. Actually, this maximize over time slices version of it is Aaron Wall a few years later. There's a couple of different ways you can define the time-dependent case. But anyway, so that happened. Then there was work by Faulkner, Lukovic, and Madicina that sort of realized this term should be in there. And actually, this minimizing over the whole thing is Engelhardt and Wall. But again, they did it for the whole time-dependent case. So this is sort of just like a special case that wasn't known before the more general case from a historical point of view.
So this whole formula is valid only for static states?
Yes. It's valid if you pick the right Cauchy slice. Okay. If it's a static case, the right Cauchy slice is just a static Cauchy slice. Time reflection symmetry is the time reflection symmetric Cauchy slice. In general, it's the Cauchy slice that maximizes this minimum. Well, that's degenerate, but it will contain a unique surface.
So still a general formula.
Yeah, if interpreted in that way. Exactly. Yeah. It's not like yeah, exactly.
Thank you.
And the issues with the time dependent stuff are not really going to be talked about. So, but really spiritually, it's a general formula. Okay. Great. So there's a very closely related idea that sort of developed from it to this relationship to the entropy to the area plus entropy of the surface. And that's that more generally, if we look at the state on that region, we have some reduced density matrix, and that reduced density matrix is in some way encoding this region little b on the bulk. So if you know what that density matrix is, at least to some degree, you know what that region little b at the bulk is, and vice versa. Okay, so the duality is between, sometimes called subregion duality. There's an ADS CFT style duality between this subregion, this CFT, and this subregion of ADS. So this statement can sort of be precisely understood in terms of quantum error correcting codes, and a decent part of that talk is going to be devoted to that. But for the moment, I'm just going to leave it slightly vague what it means, because sort of the precise meaning is going to be important, and the precise meaning has evolved over time. And really, I think this paper is the first to nail down the precise meaning. We've got gradually more precise over time. So there's a sort of obvious observation, but it turns out to be important, that if we look at this surface region big B bar, the complement of the region big B, okay, and then we apply the same quantum minimal surface formula that we applied before, as long as our state of our CFT and of the bulk quantum field theory are both pure, then the region that we will get, the sort of region dual to big B bar, is in fact this region little b bar that's the complement of little b. Okay, so it's sort of easy to see this, like the entropy of complementary regions in a pure state is the same, and so the area of the edge between them is the same, and so it just ends up being the same minimization in different words. So this is an important idea, which is that, at least for pure states, we have what's called complementary reconstruction. So everything in the bulk is either encoded in big B, or it's encoded in big B rather. Nothing, say, in the middle that isn't encoded in either. Certainly nothing encoded in both, because that's not allowed by the no cloning theorem.
Is there anything special about twofold decomposition of the boundary?
Yeah, I mean, if I did a threefold decomposition, then the complement of the entanglement wedge of the union of any two would be the complement of the entanglement wedge. But if I had, say, three, let's say I just had three, then I'd have maybe three surfaces like this and this and this. There would be a region in the middle that is not encoded in any one of the three regions on their own, and instead will be encoded in any pair of the three regions. So this was actually the original thing that made people realize there's sort of quantum error correction getting involved. Famous paper by Almiri, Dong, and Harlow back in about 2014, the first of that. So this is special to two regions. Okay, so there was a beautiful paper by Harlow in 2016, where the sort of basically the summary of what he said is that this may seem like it's something about gravity, but we can actually just forget about gravity and just consider an arbitrary quantum error correcting code, where, in a precise sense that he defined, anything, we sort of have two logical subsystems, that are encoded, little b and little b bar, and we just assume that anything in little b is encoded in some physical subsystem big B, and similarly anything in little b bar is encoded in some physical subsystem big B bar. So we're just abstracting away this idea of complementary recovery, completely forgetting about gravity and just thinking about the quantum error correction properties. And then what he showed is that any such code will obey a formula that looks very, very similar to the quantum minimal surface prescription that I showed before. Okay, so the entropy of big B, sort of the entropy of some physical qubits that can be used to recover a little b, is given for any state psi by the entropy of the qubits in little b plus some extra constant term that I've called A, because it's analogous to this extra area term in ADS CFT.
What is the psi again? I missed that.
Psi is like the analog of a bulk state. It's some state in your code space So let me actually just write down very quickly what a quantum error correcting code looks like.
Was about B side.
Oh, sorry, yeah. So let me write that. So in a quantum error correcting code, you can think of as an isometry. So we can think we have two subsystems, B and B bar, and then there's some isometry V that maps them. You can think of this as the map from the bulk state on little b and little b bar onto a boundary state on big B and big B bar. I'll make this more precise in a minute. Okay, so it's like V psi is like the CFT state, psi is like the bulk quantum field theory state. Okay. Okay. So yeah, seemingly this complementary recovery doesn't have anything to do with gravity. It's just can be a fact about quantum error correction. But we get out this thing that looks an awful lot like the formula we had in gravity. In fact, the converse is true. If we have some code, some isometry B from little b bar to big B bar, such that this equation is satisfied for any state, then it will have quantum error correction, it will have complementary recovery. Yep.
Can you assign any geometrical concept for A here?
No, at the moment, A is literally just a number. Okay, but I think that's exactly the right question. We're not gonna get all the way to actually having a like Riemannian geometry or something. But you can think of this as the very, very beginnings of having some sort of emergent bulk geometry for this quantum error correcting code. So that I've sort of put a couple of comments here. So this sort of seemingly central feature in gravity, arguably the most important equation in all of ADS-CFT, you can certainly make a case for that, is actually just coming from nothing about super Yang-Mills, anything, large N CFTs, anything like that at all. It's just coming from quantum error correction features of some encoding logical state in a physical state.
What does A depend on?
A will depend on the code B, right? So we can imagine different codes, different. Yeah, I'm going to be more precise about what V is in a minute, but that's what it depends on. What your quantum error correcting code is. Each quantum error correcting code will have a different A. And he gave some definition of A for any quantum error correcting code with complementary recovery. Okay.
Does all this have anything to do with Linde's idea about how to relate reality to entropy?
I don't think so. Linde's idea, yeah,
Whatever happened to Linde's idea?
I don't know. I never understood it.
Careful.
I don't know. I like Eric a lot. He's a very smart guy, but I never put much effort in trying to understand it, and I never understood it. So I'm not the person to ask. Yeah. Okay. So if you're willing to be very flowery and ambitious, you could say that the fact that any quantum error correction code has this single number A that is analogous to the area of the surface, sort of the beginnings of an emergent bulk that we're getting without having anything more than just some quantum error correction. That's obviously a bit, some might say it's taking a bit too far, given it's just a single number, but we'll get a bit more of that than that later. Okay. Why is this not working? Okay, we're working.
Yeah, okay.
Okay.
Crazy day today.
Great. So at a very high level summary, what I'm going to do in this talk is going to be almost, if the one sentence summary is almost exactly the same as the one sentence summary you could have given of Harlow's paper in 2016. So we didn't just get scooped by 5 years. We're trying to build on Daniel's really great work and push it a bit further. So there's one big thing that was missing in the summary I just gave of Daniel's thing. And that's that you may have noticed we had no minimization over little b, right? No, find the little b that happens to have the smallest entropy and go with that. And there's a reason for that, which is just Harlow in his assumptions of his theorem assumes that the same b applies for same little b applies for all states psi, all bulk states to consider. So you can think of this as having, some code space where just the minimization is the same no matter what state you can consider. And in that case, you can forget about any other possible B's because there's only one that matters. So that's why he has no minimization. Yep.
If I consider a perturbative description of the bulk state,
Yep.
does it do any good to me in this picture, or do I have to do something more sophisticated?
Yeah, so if I take the classical limit and I have all my sort of code space stays the same size as I take the classical limit, then yes. So then I had these two terms. I had an A over 4G, right? That's an order 1 over G thing. And then I had an S that's just like order 1. And so then the minimization will just care about the minimization over this thing. And as long as the geometry is like fixed, it's the same for all states in states I'm considering, then you can just sort of forget about this when I do the minimization, and there'll be the same little b for all of that.
Well, what is b in that case?
So
if let's say that I take a scalar, 2-point function.
Yeah.
What corresponds to the b?
Little b. So what corresponds to little b will depend on little b is a region of the bulk, right? So say I had some big boundary region, big B, then I have a little b that maybe takes up half the bulk. And then this S of little b is just the entanglement entropy of the scalar field in that half of the bulk, right? That will have some reduced state that's mixed. It will be like a, in this case, like a thermal Rindler state, and it will have some entanglement. Okay, so the reason I don't want to say you can do that is, well, I'll give a couple of examples in a minute of why it's important to be able to allow it to change. Okay, so yeah, in general, in gravity, this is just not true. Even if you go in a certain sense to the semi-classical limit, then you can still have the region little b depend on the state in your code space. So let me give sort of two examples. First goes back to a paper I wrote with Patrick Hayden in 2019. So let's consider a black hole sitting in the middle of ADS. Okay, and then and then we're going to consider some boundary region big B. This diagram is inconsistent with the text I write, so please imagine the big B takes up more than half the boundary here. Okay, it's not drawn to scale, but big B is going to be over half the boundary. The black hole is sitting in the middle. And then our code space, our sort of set of bulk states we're going to be considering will include all microstates of this black hole sitting in the middle. Okay, let's now consider two different states. In one of them, this black hole is just going to be in some fixed pure microstate. Okay, in that case, this surface going around the back has a smaller area. As I said, this is really more than half the boundary. It's not to scale. I needed to change my argument because I used the wrong diagram. This has smaller area than this. And so that means the little b that minimizes everything will include the black hole. It will be this entire region, including what I call little b here and what I call little b prime. Okay. But I could also consider a state where the black hole is in some highly mixed state. Maybe it's in the sort of thermal ensemble state. And in that case, there's this really large contribution to the entropy of this big region that comes from the bulk entropy of that black hole. Okay, so that will just be the Bekenstein-Hawkey entropy in this case, which is not just some like order 1 thing. It's order 1 over G. It can compete with this area term. Okay. So if I choose my region B correctly, I can make it so that the area of this thing is smaller than the area of this plus this extra Bekenstein-Hawkey entropy. And so that means that for that highly mixed state, there's a smaller entanglement wedge that just contains this little sliver to the right of the black hole. Okay, so different states in the code space are able to have different entanglement wedges, even in the limit where it's sort of semi-classical limit, if our code space is getting bigger as we take that limit. Another example, which is probably more important these days, which is you guys may have heard about. In 2019, there was a lot of excitement about applying these entanglement wedge calculations to evaporating black holes, and that's a bit more complicated because it's a time-dependent state, and so it's technically outside the scope of what I've defined. But the basic story is that you have a very large, an order 1 over g amount of entanglement between Hawking radiation and stuff inside the interior of the black hole. Okay, and considering a state where you have that entanglement is able to, it's again order 1 over g, it's able to compute with the area term, and it changes what the quantum minimal surface, in that case the quantum extremal surface, ends up being. So you have exactly the same thing of some large amount of bulk entropy that's able to compete with the area term and mean that different bulk states have different entanglement wedges. So we really do want to be able to deal with this situation where the entanglement wedge depends on state. Okay, so I'm always ready to sort of lay out the goal of the talk. Half the talk we have to build up to even defining what we're going to try to do. But let me make a brief comment about what happened to that notion of complementary recovery now that we have different entanglement wedges for different states. In particular, for pure states, it's still, you still have complementary entanglement wedges, as I said. But if we consider that highly mixed black hole state, where this black hole is just in a thermal mixed state, then as I said, big B just encodes this little b out to the right here. But it's also the case that big B bar just encodes this little b bar out to the right, because again, it doesn't want to have this huge contribution from the entropy of the black hole when it does the minimization over area plus bulk entropy, right? It's better for it to exclude the black hole as well. So if we just define complementary recovery in terms of big B and big B bar, then for mixed states, it's just not true when you have this large amount of bulk entropy. You can have this no man's land in the middle that isn't encoded in either big B or big B bar. Yep.
In this case, the whole system is not interested in.
Yes.
So back to on this.
There's no reason you should expect them to be the same. I'm just pointing out, here's an explicit example where they're not. And in Harlow's theorem, because he needed little b to be the same in every case, it was important that you did have complementary recovery even for mixed states. Okay. So it turns out there's still an important notion which even for mixed states you do have complementary recovery, and that's just that we can always purify our mixed state by using some auxiliary system that we normally call a reference system in quantum information. So rather than considering this rho b bar, the mixed state of the black hole, consider the purification psi big B bar, big R bar. Okay, and then we, rather than considering the complement of big B to be just big B bar, we can consider it to be big B bar and R bar. Okay, and then we can apply a slight generalization of the quantum minimal surface prescription that computes the entropy of big B bar, big R bar for us. All that changes is you have to stick R in this bulk entropy term. R bar, sorry, that's again a typo. And so what happens is that now we do have the thing where S of little b bar R is equal to S of little b, because the purified bulk status is obviously pure. And so it does end up being the case that if we do this minimization, then we get little b bar and little b prime. We do get the black hole, because the black hole is now entangled with the reference system, so that decreases bulk entropy rather than increases it. So we do have complementary recovery as long as we think about this purification side. So I'm going to use a lot of statements in this talk are going to involve purifications of mixed states, because that's sort of the right thing to think about rather than the mixed state itself. Okay. Yep.
So the R bar should adjust it as the boundary for the purification.
Yeah, you can think of it that way. Yeah. Yeah, that's probably the nice way to think about it. That's how I tend to think about it. Well, yeah, one way to think about it, you can imagine just the R bar being some second holographic system, and then this R bar would be the boundary of that second holographic system, and this R bar would be the bulk of that second holographic system. But you can also just think of it as you don't have to do that. You can just think of it as a non-holographic system and just say this is a slight generalization of the previous formula, but it's sort of the obvious generalization. This generalization again goes back to my paper in 2018 with Patrick Hayden, And in fact, if you're wanting to compute the page curve of Hawking radiation, really you're using this formula, actually applied to the second special case where you only have like an R, you don't have a part of the boundary, right? That the Hawking radiation, if it's escaped into some auxiliary system, then to compute it, you need to use this formula. So in that context, this is sometimes known as the island formula.
So can I ask a question?
Yep.
So you are not changing the region B bar, right? You're not physically changing the region.
Big B bar, no, I'm saying we're considering big B bar plus, we're computing the entropy of a different reduced density matrix, right? The reduced density matrix of big B bar has one entropy, and there's another reduced density matrix that's on big B bar tensored to this auxiliary reference system that will have a different entropy that's computed by a slightly different formula, namely this thing. Okay, awesome. Okay, so the goal of this talk is going to be to generalize Harlow's theorem, which is a really beautiful theorem, one of the coolest results in my mind in the last 5-10 years, to allow the entanglement wedge to be different for different states, to allow this much more general class of things. So this is going to end up giving us sort of a richer class of quantum error correcting codes, because we can have quantum error correcting codes where the complementary recovery depends on the state. I'll define what that means in a bit. It's also going to give us richer sort of emergent geometries, because we're not just going to have one area anymore, right? Because there's going to be different surfaces that can be doing the minimization. So we're going to have like a whole set of areas associated to different surfaces. Okay, so but to do this, we're really going to need to do two things, very related to what I just said. The first is that Harlow's definition of area only made sense for the specific subsystem little b that was the subsystem reconstructible from big B. Like and it only made sense for codes that actually had complementary reconstruction. So we're going to need to generalize that definition. And the other thing we're going to need to do is sort of give a precise definition of what it means to be able to do reconstruction when different states have a different reconstructible region. So normally in quantum error correction, you just assume there's some like subsystems or fixed subsystem that's reconstructible, and it doesn't matter at all what state you're talking about. Like you don't know the state you're trying to reconstruct. That's the whole point. So this is going to be a pretty big generalization, but it's there's some load of previous work on this, both by something called state-specific reconstruction, state-dependent reconstruction. It's important early work by Papadimos and Raju. Also work by me and Patrick Hayden, me and Chris Akers, and this is something I've thought about for a few years. Okay, so let me now be sort of very precise about the setup we're going to have and what the formalism we're going to work with. Okay, so we're just going to consider, as I've been saying, some very general quantum error correcting code. Let me now be completely precise about what I mean by that. Going to have a load of input subsystems all tensored together. These are going to represent all the different points in the bulk. Okay, you can imagine some discretization of the bulk or something, and so we have all these different bulk points, and our bulk Hilbert space is just a tensor product of that. Okay, and then there's going to be some map, linear map V, which for the moment at least will take to be an isometry. It's going to map that bulk state to the corresponding CFT boundary state, which is a tensor product. I mean, really it's a tensor product of local points across the boundary, but we're just going to split it into the two regions, big B bar. Okay, again, quantum field theory, you don't really have this tensor product factorization. You have von Neumann algebras, blah, blah, blah. There's a lot you can say about that. But the intuition from finite dimensional quantum systems is generally very good. So we're not going to worry about any of those issues. And probably you could generalize these results to them if you put in enough work. Okay, so now we need to define an area associated to any, say we have these set of 3 bulk subsystems, then we want to define the area of the small sort of a surface bounding B that just includes those 3 subsystems and nothing else. Maybe it wiggles around like that. Okay. So how are we going to do that? This is actually entirely due to my collaborator, Chris Akers. It's a really nice idea by him. It's very, very simple. What we're going to do is use this thing called the Choi-Jamalkowski state. just a particular state defined for any isometry B. Very simple. Just take a product of maximally entangled states on these little bi's tensored with some other system little ri's. So say little b1 is maximally entangled with little r1, little b2 is maximally entangled with little r2, and so on up to little bn is maximally entangled with little rn. Then we take all the little b systems and we just apply this isometry b to them. So now we have a state on big B bar, and all these little r's, and we call this the Trigeminal-Kowski state. Okay. And then I'm just going to define the area of any set of little b's, say little b1, little b3, little b5, to be the entropy in this fixed Trigeminal-Kowski state of big B plus the corresponding little r's. So these both represent a little set of little b's and a corresponding set of little r's. So say area of b1, b3, b5 would be the entropy of big B together with r1, r3, and r5. Okay, is that definition clear to people? It's going to be reasonably important. So, so this area, does not depend on some choice of state. It's defined using one particular state, but it's just, that is a unique state for this isometry B. And yeah, one thing I should say is it does depend explicitly on this region big B, and that's just because our surface needs to sort of be anchored on big B, right? If this so-called homology constraint that we only consider surfaces anchored on big B. Okay, so that's the reason for that. So let me just make a brief comment that you can show this area in actual ADS CFT, if you try to apply it to actual ADS CFT, won't always be equal to the geometric area in the bulk. Okay, but what will be true is that if your surface, your region little b, can ever be a quantum minimal surface for any state ket psi, then this area will be equal to the geometric area. If your surface is just some very weird wiggly surface that there's no state psi that it ever minimizes area plus bulk entropy, then instead this is just a lower bound on the geometric area. But what that means is that if we're only caring about areas in the context of this quantum minimal surface description, then it sort of doesn't matter if you increase the area of something that is never minimal anyway, right? You're just making it like even more never minimal. You're even certainly never minimal. So what we say is that this is sort of a functionally unique definition of area in the context of a quantum minimal surface description. In terms of the things you care about for the quantum minimal surface description, namely surfaces that actually minimize the area, then it determines everything uniquely. Okay, so the other thing we're going to need is this notion of what it means to have complementary reconstruction for some quantum error correcting code when different states have different reconstructed regions. Okay, and in particular, what's going to happen is that to be able to do the reconstruction, you're going to sort of need to know what the state is, right? Otherwise, you don't even know whether you can reconstruct the region at all. That's the only way you're going to be able to do the reconstruction. But before we get to that, I'm just going to sort of spend a bit of time just talking about like ordinary quantum error correction and what it is and what it means, and gradually generalize our way to the thing we actually care about. Okay, so this is, slide would be very, very familiar to quantum information audience, to people who focus on high energy. It may not be so obvious. But what is a quantum error correcting code? Don't try to read this full theorem. This is just, I will point out the relevant bits of it. The sort of standard definition of a quantum error correcting code. So we have a map, an isometry V from a code space to a tensor product of HB and HB bar, such that there exists some other isometry that I call W, starting with our state in the code space, applying the isometry B, and then applying our isometry W that just maps from big B. We lost access to big B bar, but just by looking at big B, we can get back the original state on the code subspace. So there's an isometry that sort of undoes the noise of losing access to big B bar and gets you back the original state on big B. Okay, so this is sort of the textbook definition you will see of quantum error correction code. in fact, even in like quantum computing or something, this isn't actually the definition you care about, because once you've done this, once you've sort of got back your original state, then you no longer have any quantum error correction anymore. So then if an error happens, you're screwed. So you never actually want to do this. You never actually want to decode the state, to decode the logical state. What you instead want to do is be able to do useful things to the logical state by acting with the physical state, big B. Okay. So there's a couple of different things you can do. One is you can demand that if you want to do some measurement on your logical state, some measurement on H code, then there's a measurement on just HB, big B, without any access to H big B bar, that will do the same measurement, that will have the same effect on all states in the code space. So that's this condition here. It's also roughly this condition here. This sort of naively seems slightly stronger, but in fact, these four conditions are all equivalent to one another. So if you have one of those conditions, you have any of the others. So as a final definition, so you can instead think, rather than thinking about like measurements on big B, you can think about, say we want to implement some quantum computing algorithm on our code space. We want to do some unitary evolution. Okay, then we want to be able to do that same unitary evolution just using big B. Okay, without having any access to big B bar, because that's an environment that has been lost to noise or whatever. So that's this condition, that for any U code, then we can find a U big B that's a reconstruction of that U code, that's implements that U code for us, such that UB applied to V of psi does the same thing as applying, gives the same state as applying V to U code acting on psi. Okay, just means that this is like simulates this U code. Okay, so as I say, in this case, all four of these things totally equivalent. Will turn out that this last definition is going to be the nicest one to generalize for our purposes. So there's a slight generalization of quantum error correction you can do. It's called subsystem quantum error correction, where your H code splits into a tensor product of H little b and H little b bar. So this is in fact what Daniel Harlow was using in his theorem. So in this case, rather than requiring that using HB, there's an isometry that gets you back all of H code, all it has to do is get back the reduced state on little b. Okay, all it has to do is recover that subsystem of the logical code space. So this is saying you can recover, get back the state on little b from the state on big B. It's again an exactly analogous statement, saying equivalent statements saying that measurements on big B can simulate measurements just on little b, but not all measurements on the code space now, just measurements on little b. And then finally, that any unitary evolution just on little b, any u little b can be simulated by u big B. Okay, so now we're finally getting there. So that's one way you could direction you can generalize quantum error correction. It's another generalization, sort of orthogonal direction you can generalize it, and that's starting to get towards this idea that your reconstruction depends on the state. So this is something that Patrick Hayden and I called 0-bit codes, though they existed before that, earlier work by Patrick Hayden and Andreas Winter. And ignore these three definitions for the moment. The important one for our purposes is going to be this bottom definition. So this almost looks like, I've made it approximate for reasons I'll explain in a moment. This almost looks exactly the same as condition 4 2 slides ago, that we have some state psi and some U code, and we have a UB that does the same thing as U code acting on psi. The difference is that in this case, our UB is allowed to know what the state psi is. So in other words, in fact, for any psi, a UB big B will exist, but you're allowed to choose your U big B to depend on the psi. Different psis are allowed to have different UBs. Turns out this makes doing quantum error correction way easier if you allow this state specificity. In particular, if I have, say, 1 million qubits, I want to do ordinary quantum error correction, I need to encode that in at least 1 million qubits. In this case, you can encode those 1 million qubits in 500,000 qubits on big B, or roughly 500,000. and still be able to do this form of quantum error correction. So it's like way better. You can allow way more noise and still be able to do it. Okay, so this is exactly the sort of quantum error correction it turns out that you have in entanglement wedge reconstruction and gravity. This is like the right thing to be talking about. Yes.
So in these theorems,
Yep.
all of these different formulations, they tell you about the existence of these operators. But the proof, does it also give you a constructive?
Yeah, if you look at the proofs, we prove all these things. All the things I've just shown are well known, but we give very self-contained proofs in the paper. So if you're not familiar with all this stuff, the idea is that there's an appendix where you can sort of learn all this stuff from scratch. And yeah, so in that case, we give constructed definitions for each of these things in terms of the other conditions. So if you know what your, say, WB is here, then you can know what your pi B's are here and so on, and go around in a little cycle. Okay, so to understand what's happening in holography, we're going to need to both have this sort of state specificity, this idea that your reconstructions are allowed to depend on the state you're trying to reconstruct, and we're going to need to have some subsystems, and only certain subsystems will be constructible. It contains both those features, and clearly that's going to be easiest to do in terms of these sort of condition fours, because that's the only one that appeared in all my different theorems. Okay, so that's how we're going to generalize these things. By the way, just to make a very brief comment, the reason I suddenly put epsilons in here is that in fact, if the epsilons all have to be equal to 0, if you made everything exact, then it turns out this isn't any easier than ordinary quantum error correction I talked about before. It's only when you allow a little bit of noise, which you certainly have in gravity, you always have non-perturbative corrections that will exist, that these things become very, very different from it. That's sort of a side comment, but it's kind of important. Yep.
So when you say you need to know what the state is, do you mean like you need to know the basis or the exact state?
Need to know the exact state. So yeah, so be clear on this. So it's like, what's really happening is I have some state psi naught that I know, and I want to evolve that state in some particular way. So I just want to produce the particular state psi 1. Okay, and I'm allowed to use, all I have to do is have a unitary that takes psi naught to Ucode psi naught. On other states, it can do anything you like. We don't care about that at all. We're just demanding that it behaves a particular way on one particular state.
So the idea is that you know what the initial state is, you have then you evolve it, and you want to recover that state from part of the output.
Yes. You want to implement. So you just have part of the output, you just have big B, and you want to implement that unitary evolution of the bulk using unitary evolution on just the part of the back. That's the non-trivial task. If I was allowed to do it on the entire output, then like obviously that exists. And in fact, obviously it doesn't even need to depend on the state sign naught. You can have it work regardless. Okay. So we're going to try and combine this sort of subsystem thing with the state specificity, and so pretty obviously, we're going to want some subset of unitaries associated with a subsystem little b to be reconstructible in a state specific way. But there's a question of like which unitaries those should be. So the sort of most naive guess would be that any unitary acting within little b's within the set of subsystems that are reconstructible should be reconstructible on big B. Turns out that's a bit naive, and let me try to explain briefly why that is. So turns out if I could do that, then I could do a unitary in little b that changes what the entanglement wedge little b is, and therefore it would change the entropy of big B, and so it clearly can't be done with a unitary of big B. So let me give you an example of that. Say we have two black holes that are like highly entangled with one another. If I choose my stuff right, because they're super highly entangled, that increases the generalized entropy, area plus bulk entropy, of this surface that goes between the two. And I can make it so that this surface going around containing both of them has the smallest generalized entropy. So that's the one that defines little b for that entangled state. But now just by acting within this region with some unitary, I could disentangle those two black holes. Okay, that's easy enough to do. I can find a unitary that will do it. But then by disentangling, I changed the entropy of this generalized entropy, this smaller region. I made it so that's actually the one that's quantum minimal. Okay, and if that's quantum minimal, then only this little region is reconstructible, and that's the little region that determines the entropy. So we'll have actually changed the entropy of big B. So clearly I shouldn't be able to do that by just acting on big B with some unitary process. Okay, so the right answer instead is that we should only require unitaries to be reconstructible if they leave the entanglement structure of the state unchanged. Because if they leave the entanglement structure of the state unchanged, then they won't change little b, and you can trust that it all makes sense and is consistent. Okay, so what are those unitaries? They're just product unitaries on all the little subsystems that lie within little b. Okay, so that's going to be our definition. So we're now finally, hooray, able to reach our sort of very precise definition of what we mean by having little b encoded in big B. It says that for that state, very specific state psi, and for any product unitary u little b, product over the little subsystems within little b, then there's some unitary u big B just acting on region big B that will sort of implement that unitary for you, that will do the same thing. So we can implement that product unitary just on part of the boundary. There'll be some complicated non-product messy operator on part of the boundary, but it will only act within that part. Okay, so we're also wanting to require a notion of complementary recovery, just like Daniel did. So we're also going to require that there's a u big B bar that reconstructs any product unitary u little b bar. Okay, right, u little b bar is the complement set of subsystems to little b. And of course, really, we want to generalize this a bit more to cope with sort of mixed states in the bulk. So we're going to allow the psi to be purified with a reference system, but then because we're going to need to allow these reconstructions to act on that reference system as well as big B and big B bar. Okay, so this is the most general thing you can have. Yeah, but don't worry too much about this. You can just think about this one for pure states if you'd rather. Okay, and then finally, ready to state theorem, only 50 minutes in. Sorry that took a while. This is not the easiest paper in the world to present. I apologize. There's a lot of like technical stuff that needs to be technical background needed, but I do think the result is cool. So hopefully I've given you enough motivation to think that this result is cool. So the first condition is going to be exactly the condition I just stated, right? That there's some little b that's reconstructible from big B and one reference system, and there's little b bar that's reconstructible from big B bar and the complementary reference system. Okay, for some particular state, psi. So that is condition one. So that be true for all product unitaries on little b and little b bar. The second condition is exactly the sort of quantum minimal surface formula exactly like Daniel Harlow's thing, that you know, we defined area, remember, in terms of Geoff-Jamelkowski states. This is some specific area, and the entropy of big B and big R is given by that area plus the entropy of little b and big bar. Okay, and notice it's not enough to have this true just for the state psi. That would sort of be you could have all sorts of nonsense that would make that be true. That doesn't have any sort of quantum error correction. But we're also not going to require it be true for every single state, because in fact, even in gravity, this sort of equation is not true in all states. There are weird states where it's not true. What we're going to require is that it be true for all states related to ket psi by a product unitary. Okay, it's a very natural class given condition one. And in fact, if you know, this is in gravity, if this is true for psi, it will also be true for product unitaries applied to psi. You can show that. Okay. So you might notice that in condition two, we still don't have any minimization over little b. It's exactly like Harlow's theorem. It's just there's a little b that was the little b that appeared in terms of reconstruction. It's the same little b appearing here. But there's two things that's changed. One, we've only required that to be the little b that works for this particular psi. Different psis can have different little b's. And the other thing is that then for free, we actually get minimality. So you can actually just show that if either of condition one or two is satisfied, and hence both of them are satisfied, it's also true that for any other set of subsystems in the bulk, then the generalized entropy is bigger than the generalized entropy for little b. Okay, so this is actually the quantum minimal thing. This is the thing you would get by minimizing. So you do have minimality showing up in that. Okay. So I just have a few minutes left. So that's really, my main aim is to get you to see this theorem and hopefully appreciate something about why it's nice, why it's telling us, sort of much more general thing of how quantum gravity is related to quantum error correction. Do want to just give a hint about how the proof works. Not going to go through all the details. One thing I should say is there is an approximate version of this theorem, and that's, as I say, really the one you're interested in because everything is only approximate. It's just messier statements, so I didn't show it. But just to give you a hint of how the proof works, the real sort of heart of it is a very simple trick. Okay, and what that trick is that you take some subsystem of a state psi, you apply a hard random unitary to it, a hard random unitary acting on that subsystem. And then you apply those unitaries in coherent superposition, storing the output in storing the unitary that you applied in some auxiliary quantum system. Okay, so this thing is just some isometry, and it's pretty easy to see what it does, because if we just forget about this thing that stores which unitary applied, then we would have just applied a sort of incoherent random choice of hard random unitary, and that's always going to put this little bi into the maximally mixed state, right? It's gonna throw away all the information little bi. So basically what this has to do is it has to leave, but the global state is pure, so it has to leave this little bi maximally entangled with some subsystem of the auxiliary system I added that stored which unitary I applied. And that's indeed what it does. And in fact, what it then also does is the state psi that was previously on little bi also ends up getting moved to this maximally entangled to some subsystem of the auxiliary system. So effectively what this is it's an isometry that swaps out little bi for half of a maximally entangled state and puts the stuff that was in little bi in an auxiliary system. Okay. Very similarly, if we have sort of condition one, if we have ability to do reconstruction, we can define an isometry on big B, big R that basically does exactly the same thing. It just does it by only acting on big B and big R. In other words, by acting on big B, we extract the bulk state within some entanglement wedge little b and extract it out into an auxiliary system. So graphically, this looks something like this. So we first apply an isometry big BR. That swaps out the stuff that was in the entanglement wedge of big B into an auxiliary system and leaves the entanglement wedge of big B maximally entangled the reference system. Then we can do the same thing on the other side, right? That swaps out the stuff from here, puts it also just in an auxiliary system and leaves that entanglement wedge maximally entangled the reference system. And now this is exactly the Trigeminal state that we use to find our areas. Okay, so that's why that gets involved. That's why you can relate having that Trigeminal state to having these sort of reconstructions. So yeah, just to very quickly flash the proof of how condition one implies condition two. Don't worry too much about it. But we just apply, we know from condition one that these WBRs and WB bars exist. So they're isometries, so they don't change the entanglement entropy. So that's that equality. But then this state is just a product of Trigeminal state and the bulk state in some auxiliary system. So now we've related this boundary entropy to the combination of entropy of Trigeminal state and a bulk entropy. But of course, that Trigeminal state entropy is exactly how we defined error. So that's how we end up getting this formula. That's how you can sort of get from condition two to condition one. Yeah, the other directions work in different ways, obviously, but they involve similar tricks involving W's. So that's the sort of the key way to come up with all of these proofs. Okay, so yeah, that would just give you a very, very vague hint of the sort of maths involved and the sort of tricks involved with coming up with these proofs. But I want to end with just some final comments of like big picture. if you've got lost in the technical details, I know this talk is kind of technical. I try to make it as not technical as possible, but it's just hard with this paper. So, the sort of big takeaway is this idea that there's an equivalence between just having sort of quantum error correction properties, certain type of quantum error correcting code that's equivalent to entanglement reconstruction, and having some sort of formula relating areas to entropies goes well beyond the sort of baby version that Harlow found. Okay, Harlow's version is just about this very simple code spaces where the entanglement wedge is just fixed. It has no dynamical thing that depends on state, but we can go way beyond that and we still get something that works exactly the same way. So any code with these particular quantum complementary state-specific quantum error correction properties, I took 5 slides to even define, and probably half of you have forgotten definition now. It's actually a very general thing that you can think of ordinary quantum error correction or any of the other definitions I gave just as special cases of these very general codes. Has a sort of associated emergent geometry where you have for any set of logical subsystems, you have an area bounding that set, and those areas determine this quantum minimal surface description. So importantly, the theorem is robust to errors. The proof gets more horrible, even the theorem statement gets a bit more horrible. We look at it in the paper if you really want to, for whatever reason. But it is very important that the theorem is robust to errors. Like a lot of the early proofs of entanglement reconstruction, if you tried to take that proof, you could have the conditions of the theorem still be true approximately, and the conclusions just would not be true, not remotely true. So you really want to make sure that your proof is robust, even if the details of the errors are just annoying and boring. Much more excitingly, I haven't talked about this at all, but if you're really interested in these things, I encourage you to look at it at least a bit. Turns out that this map V for the quantum error correction code doesn't actually need to be an isometry. Any linear map that satisfies these conditions will work. And in fact, that's what you need to sort of understand the interior of the black holes after the page time. Because after the page time, you sort of have more information inside the black hole than the physical information that describes the black hole. And so that's why you have non-isometric linear maps showing up. There's just not space to fit all that information in. And so there's exciting corrections to the black hole information problem. If you want to understand why, if you're familiar with the 2019 papers, then there was a big objection at the time that we were using this sort of Hawking state, this semi-classical state where there was this huge amount of entanglement between Hawking radiation and the interior of the black hole. We were using it to compute an entropy that says there wasn't actually that huge amount of entanglement, and hence that state was just wrong. And people say, how are you using the wrong state to compute the right thing? That doesn't make sense. The right way to think about it, I think, is that it's because the right state is an encoding of that naive Hawking state in this state-specific sense. And it's that encoding that means you can apply these holographic entropy prescriptions to it. So that is going to be discussed in upcoming work with various people in much more detail. So we decided not to talk about it too much in this paper. And we're going to write a much bigger paper on it with these collaborators. That's all I have to say. Thank you very much for listening.
Yeah, thank you very much, Geoff, for this very nice talk. So are there any questions here from the audience? We had already some, but please.
Can I ask a question? So
Yep.
the reference system R that you talked about,
Yep.
can I think of it as some CFD brought to the user of the AES?
You can if you want, but fundamentally it can be anything.
I mean, would that be
That would be an example, yeah. Any non-holographic, or even, as I say, you can think of it as a holographic system and then have like the both. But yeah, just any non-holographic system that you happen to be interested in computing the entropy of, and yeah, presumably you want it to be entangled with the bulk, because otherwise it's like not interesting. It's not going to have any correlation. It's not going to affect what can be reconstructed. But it's a very non-trivial point that sort of, you might think, if we have sort of psi here that's entangled with a reference system, and we're just trying to, but But our U here, our U little b, is not acting on the reference system at all, right? It might not seem obvious that having your reconstruction act on the reference system as well can actually help, but it just can. Yeah, that's something you just have to sort of work through an example or something to see, but it very generically is true that by knowing what the state R is, you learn more about the state on little b, and that helps you reconstruct the thing on little b is basically the right thing. So the entanglement helps you know more information, which then lets you do the reconstruction more easily.
So is that, I mean, the fact that when people, try to prove resolve the information paradox, they have to couple the ADS to the ESP. Is it because all these proofs fundamentally depend on a reference system? Is it? I
think at the simplest level, that is really just about the fact that if I have a big black hole in ADS and I want it to evaporate, then I need to couple it to a bath, or it just won't evaporate. Right? If I have reflecting boundary conditions, my black hole is not going to get smaller over time.
But I'm saying that you want to, let's say, try to resolve the information paradox in some other
in flat space, you can do the calculations without having any bath, or in ADS, just take a really small black hole. Some black holes small enough it'll evaporate before the Hawking radiation reflects back in. Then that's it.
Need a reference system.
Yeah. The reference system was really included in order to be able to like deal with those cases where it's coupled to a bath and so on, because they're important because large ADS black holes, you need them. But that was just about having the theorem be as general as possible. Let me go back to the theorem. Okay, so this state psi here, we allow it to be entangled with some reference systems, but I could just take a psi. I could just take those reference systems trivial, or I could just take a pure state psi in H code, and the theorem will still go through in exactly the same way. And then this entire theorem would have no reference to a reference system at all. I'm just trying to make the theorem more general by allowing that to happen. Okay. Yeah. So if you confuse what the hell the point of reference systems are and you don't like thinking about them, then just delete any reference to R bar here and assume this is just some pure state in the code space in the bulk, and then everything makes sense.
Can I ask a question?
Yep.
So is this a prescription for the quantum extremal surfaces? How easily is it generalizable to Renier entropies?
Great. So that's a very good question. Yeah, the in practice or in principle? In principle, it certainly is, and in some ways, Renier entropies are easier to compute because they're just a replica trick with no sort of analytic continuation or anything. In practice, you can't compute the Renier entropies just by looking at the sort of classical saddle point geometry. Instead, you have to do a replica trick and look at the back reacted geometry. So yeah, basically the answer is in practice they're very hard because you have non-trivial back reaction. But sort of in principle they're easier because yeah.
I see.
Yeah. There's some assumptions you have to make to derive this prescription for the von Neumann entropy, and those assumptions sometimes are wrong, and that's why this prescription doesn't always work. It just works for a large class of states. For the Renier entropies, there's just an explicit computation you can do that will just in with the gravitational path integral that in principle will just spit out the right answer. It's just a hard computation to do because it involves back reactive geometry.
Oh, I see what you're saying. Okay. Thanks.
Cool.
Yep. So the statement of the theorem is that if for a state condition 1 is true, then equivalently 2 should also be true, and then the third condition follows.
You go for free. Yeah.
Right. Do you have any way of filtering which states would have these conditions being true?
That's a great question. So in general, for a general code, yeah. So one thing you might want to be true is you might want to say that if this minimality thing was true, then you'd have both of these things be true. Okay. That's not even true in the gravity. Okay, so even in gravity, this thing does not imply these two. So that was a paper Chris and I put out like in 2020, showing that just sometimes it's just totally wrong. There is a stronger condition. So I actually cut down this theorem slightly from the one in the paper. In the one in the paper, we have an intermediate one that is implied by these conditions and implies this last condition. That is sort of similar to this minimality thing, but instead of in terms of von Neumann entropies, it's in terms of what's called min-max entropies, which are a different type of entropy. Okay, so that one in gravity is like a sufficient condition to imply condition 1 and 2. Okay, and in things like random tensor networks and nice toy models of quantum gravity. But again, if I just have some totally random code, that's a condition that like doesn't really know enough about the details of the code to be able to get condition 1 and 2. So it's like for nice codes, it's a sufficient condition. For all codes, it's like a necessary condition. You could probably come up with like nice conditions, some property of the code, like together with that is like enough. Like it's a random tensor network code, it's a holographic code. I would be surprised if there's a nice condition that like just directly gets any time these first two conditions satisfied would like it's actually equivalent to them that sort of involves that condition and maybe more and something more. But certainly that condition on its own is not enough for general codes. You need something that like it's the right sort of code coming in there somewhere, right? Great.
Okay, very nice. So when there are no more questions, let me stop the recording and then let's thank our speakers for the night.
I'm still trying to